concerning bonding and structure. Let's see how the different types of bond that are formed by these inorganic compounds. Now here we shall talk more of bonding. Then when we reach in physical chemistry, we shall talk about structures, okay, of these inorganic compounds, the different structures that are formed by these compounds. That's more physical, and we see how we can draw the different structures and stuffs like that, okay. But here we shall talk about more of bonding. So in senior 2 you studied bonding, okay, and you saw the different types of bonds that are formed by these inorganic and organic compounds, okay. And I'm quite sure you defined a bond as a force of attraction that is formed between two atoms that are close to each other, and it is that force of attraction that holds these atoms in close contact, okay, especially when the two atoms react with each other. For instance, let's say atom A reacts with atom B, okay, to form this compound, maybe compound AB. Now think about how these two atoms, okay, will combine together. Which forces will keep these atoms close together such that they remain in their compound AB, okay. So therefore the electrostatic forces of attraction that will keep these atoms close together is what I refer to as a bond. You cannot see a bond, you cannot touch a bond, but it is believed it's there, and it is there indeed. For example, if you get your magnet, okay, and maybe this is the North Pole, now this is P7 work, and then you get another magnet, okay, and maybe this is the South Pole, this is P7 work. If you bring these two magnets together, you are holding them at this point and at this point. You will feel some force of attraction between these two magnets. That is if the poles are unlike. Now you cannot see this force with your eyes, okay, but it's there. So that force of attraction, that when you did the force to the two magnets will end up fusing with each other, and they are strongly bound onto each other. So now that force is identical to the force here. So that electrostatic force of attraction that will exist between these two atoms is what we refer to as a bond. And we have the different types of bonds that are formed, whereby we have covalent, depending on how a bond has been formed, covalent, we have ionic, okay, and then we have metallic, and then we have the additive bond. Now these are bonds that are involved in formation of compounds. But we also have other bonds that are formed between the molecules of compounds, or you can call them the intermolecular forces of attraction. Intermolecular forces of attraction, okay, and we shall also study them in this topic, bonding, where we shall be able to see forces such as hydrogen bonding, or a hydrogen bond, okay, hydrogen bonding, we shall be able to see forces such as van der Waals, okay, Waals, forces of attraction, and then the factors that affect each, okay, the factors that affect each and how each is formed. And if you are keen enough, you saw that this and this, they have been prominent as far as organic chemistry is concerned. So from here we shall be able to see, okay, we shall study how these forces do impact, do affect the structures of both organic and inorganic compounds. So basically this is going to be the outline, okay, of the topic. Okay, that's good. So let's talk about the first one, a covariant bond. Okay, a covariant bond. Now in case you have a question, the chat box is there. You can drop that question. I'll be happy to attend to it. So now a covariant bond, now this is just simple work, but we shall not take anything obvious. It is a force, it's a bond, or it's a force of attraction that is formed when two nonmetals share their valence electrons, okay, in a bid to form that octet structure. I think I will not use some hard language. So it is a bond that is formed by equal sharing of two or more electrons between two atoms in a molecule. And why do they share? They are aiming at forming that octet structure. And I usually try to elaborate this as, let's say you are at school and you have your birthday, and you with your birthday, it's break time, but you and your birthday, you are all broke. Sorry for that. You are all broke, but it's break time. So your birthday has some 500, some 500, and you also have some 500. Okay, but you want to have some break, man. You want to have break, but you are all broke. You have 500, your birthday has 500. So what you do is, the birthday brings the 500, and you also bring your 500, and you share, and then you buy the sumbis. Now in this case, you buy 5, let's say each sumbi is at 2k, 200, and they will add you 1, the nyongeza, and you buy the 6 sumbis. So do you see how you have benefited? You were broke, the 500 buys just 2 sumbis. Even your birthday, the 500 buys just 2 sumbis. But when you combined, you bought 5, and even nyongeza you 1. They even added you 1. Okay? Now when it comes to eating, please take note, because this example is going to be used throughout the entire 4 bonds. When it comes to eating, then you eat 3, and your birthday eats 3. You share equally the sumbis. So this is analogous to a covalent bond. Okay? Where all the 2 atoms have the valence electrons that are less than 8, and they have more than 3, so they are non-metals. Maybe you might have 6, you might have 7, you might have 5. You are a non-metal, electrons in the outermost shell. But you must have the octet structure to be stable. You need to have 8 electrons in the outermost shell to be stable. So what is going to happen if this is you, okay, with your 7 electrons in the outermost shell, okay? Let me use X to represent the electrons. If this is you with your 7 electrons in the outermost shell, and then now this is you, and then this is your body, okay? This is your body also with 7 electrons in the outermost shell, okay? Then you and your body will share that outermost energy level. They will come and share, okay, this outermost energy level, such that these 2 electrons, they pair up, but they are shared, okay, equally. So the bond that is formed as a result is a covalent. That's why it is called co. Okay, you know co-wives, co-husbands. I've never had a co-husband, but co-wives. So co, it comes from sharing. Co means sharing, and you are sharing the valence electrons. So basically it is as simple as that. And so because it is formed by sharing of the outermost electrons, okay, now there are conditions. The electrons to be shared must be unpaired with opposite spins. That's obvious case. Otherwise, if they are not, then maybe let me try to illustrate this. If maybe this is atom A and this is its outermost electron, okay, maybe it has this paired, and this, then it has this. Then the outermost electron that is going to share with another atom B, okay, maybe this is atom B, and then this is atom B, this is its outermost electron. So the 2 atoms to be shared must be unpaired, like how you can see here, okay, they must be unpaired. But as if that's not enough, the 2 must be parallel, but with opposite spins. This one should be facing down, and this one should be facing up. The alpha Bowes principle. Otherwise, if you don't, then they cannot pair up. Okay? Now, since they have opposite and parallel spins, then they will be free to pair up. Not so? Yes. So that's what this one means. So each atom contributes equal number of electrons so that the atomic orbitals do overlap, and when they do overlap, then the electrons will be paired. Okay? And so these paired electrons will appear kinda stable than the unpaired one. So for example, you can see ammonia, the nitrogen. What is the atomic number of nitrogen, for instance? This is ammonia. Nitrogen, is it 7? Yes, 2 to 5. So it has 5 electrons in the outermost shell. Now this is olive. Let's use what we know. This is kiddish. So this is ammonia, and ammonia is 7. So it is 1s2, then 2s2, and then 2p1. 2p1, 2p3. So you can see the outermost energy level, the P is half filled. And so the P needs how many? It needs 3 electrons to become stable. And so therefore hydrogen, which is also half filled with 1 electron in its orbital, the one electron will come and pair with one of P, and then another hydrogen atom also pairs with this, and then another hydrogen atom also pairs with this, and the result is you form ammonia, which is NH3. Now for ammonium ions, NH4, we shall see. Okay, we shall see how ammonium ions are formed when we reach there, when we reach the coordinate bond. For chlorine, same case. Chlorine is 17, okay, which is 1s2, 2s2, and then 2p, 2p6, and then from 2p6, so this is 10 covered, and then you go to 3s2, and then 3p5, so this is chlorine. So now it needs just one electron to become full, to become stable, to have that octet structure, to fulfill the octet rule. So now, what is it going to do? Since you cannot easily, then the two chloride atoms, they will come together and be like, man, you see? You see? It's like, this is just for fun, This is just for fun. It's like, I heard that, I think it was social media, the two Kasirus, I don't know how to call Kasiru in English, that two guys who are just there, they met each other, and then they were like, you are single, I'm single. I'm Kasiru, you are Kasiru. I'm dumb, you are dumb. Why don't we... How I wish you were able to see. So, even these ones, that's how it is. So you can see. So one chloride atom approaches the other and then be like, man, you are lacking one electron, I'm lacking one electron. Why don't we... and boom. So the two end up sharing their outermost electrons to form a covalent bond. So the same case with methane, the same case with carbon dioxide. However, with methane, there is some hybridization where you promote, and we explained it in organic chemistry. You can go and watch our video. So you promote, and then after promoting, then you share. Okay? You share. So basically, that's how simple a covalent bond is. So basically, that's a covalent bond, and that's how it is. So let's now talk about the polarity and the polar and non-polar covalent bonds. So like we said, these covalent bonds, they are formed by sharing of the valence electrons, and you share equally, equal sharing, okay, of these valence electrons or outermost electrons. Now assuming if the sharing is between two atoms and the atoms have different electronegativities, you know what electronegativity is? Yes, that tendency to attract the bonding electrons between two atoms covalently bonded together. Yes, it is assumed that when you share, then the two electrons must be equally shared. But now, the two atoms, one is more electronegative than the other. Okay? But you are sharing the electrons. So the one that is more electronegative than the other is going to withdraw the bonding electrons towards itself, okay, from the other atom that is less electronegative. Have a look at this. So we said A okay, is going to combine with B, okay, to form a compound AB. But assuming B is more electronegative than A, okay, this concept is good. This concept is good even in organic chemistry to explain the different behaviors of certain organic compounds. You need to understand this concept right from first principle, not cramming. Me, I hate cramming. Understand from the first principles. So if assuming B is more electronegative than A, so what does that mean? Atom B is going to attract the bonding electrons more to itself, okay, than atom A. Not so? So what is going to happen? You form this compound that is formed, it will have an equal distribution of the bonding electrons between the two atoms, such that the electron crowd will be more to B than to how it is to A. Because the B has attracted all the electrons towards itself. Okay? And so as a result, you form your compound that is kinda polarized, whereby the B will be partially negative because it has attracted all the electrons, and the A will be partially positive, okay, because it lost its electrons. And so you form a polar covalent bond. Why polar? Because the bond is polarized, okay, and this one has a big impact on the overall chemistry of this molecule, okay. It has a big impact on the overall chemistry of this compound. Not so? Yes. So for instance, carbon dioxide and tetrachloromethane, let's have this. For example, you may have you may have your carbon dioxide, which is CO, which is another O, okay, and then you have tetrachloromethane, which is like this. You have the Cl here, you also have the Cl here, you also have the Cl here, and you also have the Cl here. Now for example, these molecules, their atoms have different electronegativities, whereby the oxygen is more electronegative than the carbon atom, okay. Even in tetrachloromethane, okay, the Cl, the chloride atom, this one, the same as this, they are more electronegative than the carbon atom. So as a result, this Cl carbon bond is going to be polarized. This carbon oxygen bond is going to be polarized. The bond is going to be polarized. But however, the bond is going to be polarized, but the overall chemistry, the overall molecule is going to be non-polar. Tetrachloromethane, it's non-polar. That's why it can dissolve in non-polar solvents, such as, so that's why it can dissolve non-polar compounds. The overall molecule is non-polar. The overall molecule here is non-polar, but the bonds, they are polar. Why? Because they are formed from atoms with different electronegativities. So what does that mean? What is accounting for that? It is because the molecule is symmetrical. These atoms, the way they are arranged onto this, is symmetrical in that their effect cancels out. Okay? They do counteract each other. In that, you have a look at this. If this chloride atom pulls electrons towards this side, and this one pulls towards this side, and this one pulls towards this side, and this one also pulls this side towards that side, the effect of this is going to be cancelled by this chloride atom. The effect of this is also going to be cancelled by this chloride atom, such that now the overall molecule is going to appear non-polar. Okay? It's going to appear non-polar. This one, it will pull towards this side, and also this one pulls towards this side, such that the effect of this on this carbon atom is cancelled by the effect of this on the carbon atom, such that the overall molecule appears to be non-polar. So basically, it's as simple as that. So this question is common. They say briefly explain why. They will say explain the following observations. Number 1, carbon tetrachloride is non-polar. However, the individual carbon chloride bonds are polar. And you give an explanation. You account for that. So you must be in position to account for the non-polarity of the molecule. Not so? Yes. So tetra. Now for this one, for trichloromethane, the bonds are polar, but the molecule is unsymmetrical. Therefore, the overall compound is going to be polar. Now you have the H instead of the 4 Cl molecules. Okay? You have the H. And so what does that mean? The molecule is unsymmetrical. And so the overall molecule is going to be polar. So from that's polarity and covalent compounds. So let's talk about the properties of covalent bonds. Really, this one's there easy. This one's there is. You know how covalent compounds behave. They are simple molecules. Imagine carbon dioxide, chlorine, ammonia, sulfur dioxide. They are just simple molecules. Okay? They have simple molecular structures. And so basing on this, it will determine their physical properties, the boiling points, the melting points. They'll have very low boiling points. Why? Because they just have simple molecular structures. Okay? So for the simple molecules such as carbon dioxide, chlorine, ammonia, what else? Now for this one, we shall see. They are held by just weak van der Waals forces of attraction. And we shall talk about van der Waals forces of attraction. Okay? And see what are they in details. So it's because of this that they are so weak. They have weak structures. They form simple molecular structures. And so because of these simple molecular structures, these structures are easily overcome at very low temperature. That's why most of them exist as gases at room temperature. Chlorine, hydrogen, what else? Ammonia. Now for ammonia, anyway, it is a covalent compound, but it forms hydrogen bonds. What else? Carbon dioxide. They are gases at room temperature because they are held by weak van der Waals forces of attraction. But for molecules with giant atomic structures, for example, silicon dioxide and diamond, they do form a giant atomic structure. Okay? You remember the structure of diamond in Additive. Okay? You do something like this. This is carbon, and then this is another carbon, and then something of this kind. So carbon, 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 and then another one, same thing. Okay? So they have a giant atomic structure. Even with the silicon dioxide, okay? It also forms a giant atomic structures. Sand. So it is because of these structures that these compounds have very high, so high melting and boiling points. But otherwise, all covalent compounds, they are soluble in non-polar solvents and insoluble in polar solvents such as water. They are insoluble in polar compounds such as water, but readily dissolve in this polar compound. Because like dissolves like, and unlike doesn't dissolve unlike. For you to dissolve a polar compound, then you must be polar, so that you are able to break the bonds in that compound and form new bonds for the compound to dissolve. Okay? So if the new bonds can't be formed, then there is nothing. Okay? They are non-electrolyte. They don't conduct electricity because they don't have moving particles. No moving electrons, no moving ions, and so they cannot conduct electricity. Have low melting and boiling points, and they react together slowly, especially in organic compounds. So basically, these are the properties of covalent compounds, and I'm hoping you studied. You have some hint, you have some idea. Okay? Yes. So in case you have a question, please feel free to ask. So that was our covalent bond. Now let's talk about another type of bonding, which is additive or coordinate bond. And using the other example of ours, you and your body. Now, in the previous, we say that you and your body, 500 each, you are broke. Okay? You are broke, and each one brings the 500. Then you buy 10 zumbis. Sorry, that's 1K. You buy 5 zumbis, they add you 1, and that's 6. And you have benefited, man. But now in this case, still you and your friend. You and your body, this is your body. Now one of you is broke, another one is rich. Maybe you are broke. Okay? And your body is super rich. Your body has diamonds. So now, instead of now the two of you contributing 500, you're going to bring your head, your stomach, and your body is going to bring the 1K. And you buy the 5 zumbis. Okay? You buy the 5 zumbis, they add U1, okay, and that's 6. Now, when it comes to eating, you eat equally, you share equally. You eat 3, your body eats 3. I think you are broke, your body is rich, you bring your stomach, your body brings the 1K, you buy 5 zumbis, they add you 1, that's 6. You eat 3, your body eats 3. So that analogy is the same as a dative bond. Okay? So a dative bond is therefore a bond that is formed by sharing of 2 electrons, but all the 2 electrons are contributed by 1 atom. Okay? Sharing of 2 electrons, but all the 2 electrons are contributed by 1 atom. And it's a weak covalent bond that is formed between an electron-rich, this is your body, atom, and electron deficient, this is you, atom. So instead of electron, you can put here money-rich, and you put here money deficient. Okay? So the electron-rich atom is the one that donates that electron pair. And then for the electron deficient, just brings the stomach. Just brings that vacant orbital, the stomach, over which the 2 electrons will be donated. Are you getting? So the atom with lone pairs of electrons donates an electron, and it's therefore a donor atom. And then the other one is an electron acceptor atom. So for you, you are just a Sumbi acceptor, and your body is a Sumbi donor. Not so? Let's try to simplify science. And for example, you can see in ammonium ions, NH4. The 3 bonds, okay? 1, they are formed by normal overlapping. So they are normal covalent bonds. Okay? They are normal covalent bonds. Now the 4th, because nitrogen has a lone pair of electrons, and now this is you, the proton, okay, that lost its 1, bambi, poor one. You see, hydrogen has 1 electron. It has been persuaded by the chlorine, the 2 to share the outermost electrons, but you reach an instance where the chlorine, it is even now going to take away the K1, and it forms chloride ions, and now the hydrogen remains mutating, crying. The relationship has not been beneficial to the hydrogen. So now, this hydrogen will be there and finds another girlfriend. Will be like, man, come. And the girlfriend donates all the 2 electrons. Okay? And then they share those 2 electrons. Now the bond that is formed by sharing of these 2 electrons, all donated by 1 electron, by 1 atom, is known as a coordinate or dative bond. Coordinate or dative bond. Yes. You remember when we talked about that aluminium chloride, aluminium oxide, they do dimerize as one of the properties when diagonal relationship between aluminium and beryllium, the resemblance, yes, this is what we are talking about. Okay, this is aluminium chloride and this is beryllium chloride. They do dimerize.
What is dimerizing?
What is dimerizing? Dimer, di means two. Okay, then polymer, it comes from polymer. You remember polymer? You remember monomer? Mono means one, monomer. So dimer, now there are two monomers combining together to form a dimer. Okay, and they do dimerize by additive bonding. Okay, in vapor phase, both beryllium and aluminium, they are going to dimerize, they are going to form dimers. And it's a additive bond that is going to form that dimer. Whereby, you know that chlorine is rich in electrons. You can see the chlorine rich has very many lone pairs of electrons. You can have a look. And you know that aluminium, it has empty orbitals. Aluminium is 13. So this is 1s2, 2s2, and then 2p6, okay, and then 3s2 and 2p1. So you can see the 2p, it has 2px, 2py, and 2pz. So this is 2px, this is 2py, and then this is the 2pz. So the 2py and the 2pz, they are empty. There is nothing. There is nothing. Okay? But for chlorine, it has lone pairs of electrons. Imagine 3. Okay? So one of the chloride atoms, it will donate its lone pair to one of these empty orbitals. Okay? And then they share. Why? Because the aluminium, the beryllium, they have strong. For you to be able to form a complex, you must have a high charge density. You must be very small to be able to attract, to be able to accommodate those electrons donated to you. So for aluminium, yes, it is really small. Has a high polarization power, high charge density, high force. It is really small. Okay, so if this one donates the 2 electrons here in the empty p, then because of its small size, it will be able to attract and accommodate those 2 electrons. And the bond that is formed is additive bond, and it is usually represented as an arrow to show which atom donated the 2 electrons. And so the overall compound that will be formed is a dimer. Is that okay? Yes. Any queries, guys? Feel free to ask. Okay? Feel free to ask. So, since there are no questions as far as additive bonding is concerned, then we can freely talk about ionic bonding. And using the same analogy, of you and your body. So this is you. Now here you are just too broke. Too broke. And then this is your body. Okay? This is your body. And the body is just rich. Okay? Just rich. And so because you are too broke, then your body will see and be like, Bambi. Okay? And then donates you some 1K. And by the way, this 1K actually was making your body to look unstable. It was bothering him so much. This 1K that your body has donated, it was bothering him so much. It's like, imagine your body has 100, 100, 1K, 1000. Okay? Your body has 100, 1000. And then you are here, you want to buy stuff of 10K, but you have 9K, 9,000. So it becomes so easy for your body to just give you the 1K. But for you, once you get this 1K, man, you can imagine how happy you become. You happy. you happy indeed. So bring that analogy here. Okay? And actually you all become happy. This one, the 1K was bothering him so much. Even you really needed the 1K. So when this one loses the 1K, he just happy. And for you, when you also receive the 1K, man, you just happy. So bring that analogy here, okay? And that is the ionic bond. So with ionic bonding, it's a bond that is formed by transfer of electrons from an electropositive element to a more electronegative atom. You transfer the outermost electrons, okay, that are bothering you. Imagine you are sodium. You are sodium with 11. This is an example that I like using. With 11. And this will be your electronic configuration. 1s2, 2s2, okay, and then 2p6. And this is the octet structure. This is the noble gas configuration. But on top of that, then you add there the 3s1. Really, this 3s1, really, this 3s1, this one, and then you find another atom, chlorine with 17, with its electron configuration as 1s2, okay, and then 2s2, and then 2p6, okay, and then 2p6, then 3s2, and then 3p5. Really, 3p5. It needs just one electron to become stable. And this one, it needs to lose just one electron to have that octet structure. So it will be easy for this one to lose the one electron and forms a positively charged ion. Okay? And this one, it will be easy to gain this one electron and forms a negatively charged ion. And because these two ions have opposite charges, okay, when the two ions approach each other, this is the sodium ion, and then this one is also the chloride ions. Because they do have opposite charges, then the two ions will form that force of attraction that will actually bind these two ions close together. And that force of attraction is what we call the ionic bond. It is as simple as that. So, by the way, as we are studying all this covalent, think about, especially ionic, think about the factors that will determine the strength or magnitude of the ionic bond. Think about them. What will determine how strong the ionic bond is going to be? You can think about number one, how many electrons? I think how many have you contributed matters a lot. I think, think about it. Just meditate about it. Just think about it. I think how many electrons you have contributed matters a lot. And I think how strong you are going to attract each other. It also depends on the sizes. Not one, but for both atoms. For this and this. Their sizes, it also determines how strong the two atoms are going to attract each other. That if one size is maybe too big and the other and the other atom is too small, you think about that. How is the ionic bond going to be affected? Just have a glimpse. Think about it. Okay? And so in other words, it will take us to the factors that affect the strength of the ionic bond. So the electropositive atom loses electrons and becomes positively charged. Then the electronegative atom gains electrons and becomes negatively charged. And so the charges are held by strong electrostatic forces of attraction, which constitute a large continuous arrangement of oppositely charged ions, result into a giant ionic lattice. So because of these atoms, okay, these positively charged atoms, they'll be surrounded by negatively charged atoms, negatively charged ions, the same, okay, the same, negatively charged, the same, negatively charged. So even these negatively, they'll be surrounded by positive, positive, positive. Even so, in this interaction of these ions, they will be arranged to form a crystal lattice, okay, which is giant. And so because of this, most of the ionic compounds therefore will require too much heat to break such a crystal lattice. Hence, covalent compounds will have a high melting point and high boiling points. Not so? So you can recall the senior 2 work, okay, when you drew the structure of sodium chloride. So the strength, it will depend on the charge of an ion, and the charge depends on how many electrons, okay, are you using to form that ionic bond. How many electrons are you losing, in other words? If you lose 1, you have a charge of 1. If you lose 2, you have a charge of 2. If you lose 3, you have a charge of 3. And so the higher the charge, the higher the charge density. Anyway, charge density, it can be combined with the ionic radius. So the higher the charge, the higher the electrons lost, and so the higher the number of electrons that will be used to form that ionic bond. And so the stronger the bond. But for ionic radius, the smaller the atom, the stronger the force of attraction that will exist between those two atoms. And so, the stronger the force of attraction, the stronger the ionic bond that is formed. So you can think about how the boiling point is going to vary among oxides of period 2 or period 3. So you see that the oxides of the first group 1, group 2, group 3 elements, they are high. And even the boiling point is increasing from sodium. The boiling point of these oxides is increasing from sodium, okay, to magnesium to aluminium. I've said of oxides. Why? Because of these factors. The charge and also the ionic radius. However, it is oxides. But for chlorides, for instance, you find that the boiling point is decreasing from sodium to magnesium, okay, to aluminium. I mean chlorides. Now, why is this so? And why are oxides increasing? Now the difference is on the oxides. The difference is on the chlorides. How are the two different? And the difference is simple. These two, the oxygen and the chlorine, or the chloride atom, they have totally different sizes. And so we are talking about size. Think about how size is going to affect the chemistry, the physical properties of both oxides. And anyway, all that is food for thought. Think about it. Okay? So properties of ionic compounds, they are crystalline solids at room temperature. Okay? Why? Because they do have high melting point that cannot be just overcome at room temperature. And their crystals consist of infinite assembly of ions joined together in a regular pattern. And so as a result, they'll have a high melting and boiling point. Why? Due to the strong electrostatic forces of attraction, the ionic bonds that are formed by these elements, by these compounds. In fused state or molten state, they can conduct electricity. Why? It is these electrons that are lost that can conduct electricity from one position to another position. Okay? But in aqueous state, they can still conduct, because now in aqueous state they form ions, and now these ions can distribute the current from one locality to another locality. They dissolve readily in water because they are polar, they have partial charges, so they can easily dissolve in the water. And when oppositely charged ions react together in aqueous, they do it instantaneously. The reaction is instant. Okay? Within just a rubber stage, the reaction has occurred. So it is instant. Okay?